My talk will be pretty informal, actually, so everybody can follow it. There won't be anything mathematical, well, not heavily mathematical, and even in the end, there will be a couple of formulae, but just in the last couple of slides. So let's have a look at the content. So I'm going to start talking about interactive systems and components, which are the components of an interactive system. Then, in particular, I will talk about what is the system model. So the system, of course, but it's interactive. Interactive with the user. So we need to have a model of the user. And this will be when we will talk about the human memory model, because the model of the user is based actually on the memory of the user and how the processing of information occurs in the memory and then results in behavior. Actually, I will go through an example after this first introduction, which I will carry on for quite some time, and I will show how to perform my approach using a kind of interactive simulation, meaning interactive system simulation. So I simulate using these two components, the system model and the human memory model together, composed in parallel, let's say, simulate the behavior of the human in interaction with the system. And then I will show a specific kind of error which might emerge, we can discover using this kind of not only simulation, but actually we will use something more than a simulation. We will use a technique which is formal verification. Now, after this presentation based on the example, while building the example, while talking about the example, I also implicitly introduce a notation. I prefer to do it in the example rather than giving first the notation and then talking about the example, because things become more intuitive. Then I will actually summarize this notation, which is the notation that I used to model human memory, basically to model the human component. And using this notation together with the model of the system, I will actually show how basically to do formal verification. First, I will talk about formal verification well, briefly introduce a bit about formal verification of system properties, but then I will focus on interactive properties, properties of the interaction. So how we verify not only the system, whether it's correct, functionally correct or not, but also whether the system, together with the human, with a certain cognitive model, let's say, is able to satisfy properties of the interaction. So this is actually what we do in terms of human-computer interaction. But the interesting thing is that this approach can actually be also applied to psychology. So not only we can verify interactive system, formally verify interactive system, but we can also perform in silico experiments normally conducted in psychology. And this will help us to understand actually psychological theory, try to understand specific things at low level, but also understand very high level psychological theory. In particular, we could use actually model checking to understand this high level characteristics of psychological theory. So theories that basically psychologists give a kind of conceptual framework, we try to formalize it, and then we can verify whether what they say is correct or not. As you can see, this verification actually in the past has helped me to find things that the psychology didn't actually identify. And then with this kind of feedback given to the psychology, their theory can be actually improved. Okay, what do we describe? We want to describe a human and the world in which the human will act. Now, this acting could be normal behavior, everyday behavior, but also, as we will see at the beginning, especially mainly interaction with the computer system. Now, in reality, the computer systems are used to facilitate tasks that people perform normally, I mean, in their work, on their daily activity. Let's start to see what actually humans do normally. Well, some of you are philosophers. Philosophers normally says, what is the best activity for humans? To think. If you think about in computer science, we have this beautiful example of the dining philosophers. So in this example, the philosopher think. And thinking is actually the most important activity of human being. And it's at the basis of everything. Of course, for a philosopher, thinking is important by itself, but in reality, it's also important to establish certain goals which drive us in life. And in particular, these goals are used to perform actions on the world, of which we have some form of perception. So basically, the goals are implemented acting on the world based on what we perceive of this world. I mean, we have many tasks that we do during our daily life. Now, we want to give an example of such a task. For example, a cash transaction at a bank. So this is something that I want to describe without any use of computer aid, basically. So in the past, we didn't have anything. We used to go to the bank. Basically, we wanted, for example, our goal was to withdraw cash. We went to the bank, and then we have a task which consisted in filling a form, signing the form, then go to the cashier, giving this form, when requested to show ID, and then in the end, we collect the cash. So it's a very, it's interactive, but interaction basically between two people. There is no technology in between. Of course, these kind of interactions now don't exist anymore because everything is supported by technology. So we have something which is a system. So the interaction doesn't occur directly with the world, but it's mediated through a system. So the actual task, the original task, is actually changed. It's not the task we had before, but it's a new task. In fact, what is the technology we use to withdraw cash nowadays? What do? We go to the cashier? Exactly, it's an ATM. And this ATM allows us to manipulate the world, so to manipulate our account in this case, to calculate, produce. I mean, we don't see these things. We see only something of this through the interface, but the system will actually do a lot of things which we don't see interacting with the world. We'll check, for example, our credential, taking money out, and so on. So what we are interested in, we are actually not interested in all these things, the interaction between the system and the world, but we are interested in seeing the interaction between the user and this system, which is in fact a kind of interface between the user and the real world. And in fact, in this case, we have an interaction through an ATM. So the system in this example is an ATM. Now, you see the goal is the same, didn't change. What changes is the task. So the task is changing in this way. So when requested, we insert our card. Then when requested again, we enter our PIN, and we collect the cash and the card. Now, if you see these colors, I used this color for a reason. For perception, I use this color, magenta color. And green represent action that the user performs, in this case, on the interface. Okay, so let's try to focus on the interaction. Now you see, even the world in reality changes because before we had the cashier, we had the physical bank, and now we have a card, we have different things. So many things change, but we don't really consider them. We consider the system and what actually is visible in the system. Now, the system has to be modeled in some way because the model I gave here is the model of the task, for what the user has to do. Now, an example of ATM this is an example of a possible behavior of an ATM. So the first thing, it will request the card, and this request is still there until the card is inserted. Then request a PIN, still there until the PIN is entered. Then the ATM will check the credential. This is something that occurs at this level between the system and the world, the bank database. And then finally, for example, here, we deliver the cash first, and the user will collect it. And then we return the card, and the user will collect it. I mean, there are other possible sequences. In fact, normally ATM are machines which are programmable, and the bank decides also the sequence of operation, can do a lot of different selections in terms of the interface that appears to the user. Okay, now this is the example. We will go back to this example, but now I want to introduce how we describe the model of the user. And as I said, this is based mainly a model of human memory. Human memory with processing, of course, because it's important to understand how information is processed and used in order to behave, do some actions. Now, here we move to psychology. So there are a lot of theory about human memory, but generally speaking, all these theory agree that there is a certain structure in human memory, and this has been confirmed by quite a number of experiments. I mean, it's not really a structure that reflects exactly the physicality of our brain, but on the other hand, these subcomponents have been found using MRI and other techniques, being localized in some part of the brain, at least to some extent. So as a computer, in fact, our brain, our memory works having a structure in something that store the information for a short time, the short-term memory, but also the sensory memory, and something that store information for a long term, basically forever, the long-term memory. So what happens? Now, let's suppose again to have a system, which is our ATM in the example, but it can be any interface. So we have a lot of perception from the system. This perception go to the sensory memory. Sensory memory is something that is related to I mean, there are subcomponents related to various senses. So the information actually, all the information around us, whatever we see, for example, stays in our memory, in our sensory memory, our actually visual sensory memory for some time. And you have actually evidence of this. For example, if you move your hand quickly in front of your face, you see a kind of shade behind the hand, but you can also think about fireworks. Do they exist? I mean, those lines in the sky, do they exist? No, they are particles that move. What you see is actually the trace in your memory, in your sensory memory, of the trajectory of that particle. Basically, all the positions are stored there. And for a fraction of a second, about half a second, you see this line, which doesn't exist. You might even do an experiment in a dark room with the torch of your smartphone, and then rotate like this. You will see circles in the mirror if you are in front of a mirror. I did it. It works. It's very nice, actually. Anyway, said this about sensory memory. We actually are not interested in sensory memory. So imagine in our model that we have all the information in the world available. What's important for us is to which kind of information we select and we transfer to our short-term memory. So this mechanism of attention, called also selective attention, allows us to focus on some information. I mean, we have so many stimuli around us that we can't follow all of them. So in order to act, to do things in a way which allows us to function properly, we need to focus on some aspects. Now, we'll talk a bit more about that later, but for the moment, think that it's a mechanism that allows us to select what we want to put in our short memory. And our short memory is actually not only short, but actually small. We say that the capacity of short-term memory is 7 plus minus 2 chunks. This is something that has been found, I think, in 1956, doing experiments with people who actually were able to remember numbers, for example, up to 7, sometimes 5, sometimes some people 9. But basically, this is the limit. We cannot memorize more than that in this short-term memory. Now, I talk about chunks because the important thing is that it's not really the quantity in terms of bits or bytes of information, but it's important when the person is able to structure his information, a certain structure become one chunk. That's why, for example, chess players can memorize very big configuration in the chessboard because they can structure the information in a logical, meaningful way, things that a person who is not a very good player cannot do, but they can actually memorize this information. Experiments have been done with the chess players, and it has been seen, for example, that if you show them a configuration of the checkboards, which is normally occurring in a game, they will be able to memorize it without any problem. If you give a random configuration, which never occur, they will not find a way to memorize it. So there is some kind of mechanism that allows them. And in that case, their performance is exactly the same as people who don't even are able to play well chess, of course. Now, so the capacity is small, the access is rapid, but also rapid decay. So there are also a lot of theories here how long the information persists in short-term memory, but basically it persists according to the latest beliefs about only 2-3 seconds, very short time. It's amazing to think about it, but it is like this. Now, of course, this information at some point, if it tests information, for example, when we study that we want to remember, we have some kind of mechanism to try to make it more persistent and actually to transfer in what is called long-term memory. And the process to do it is rehearsal. Now, the most basic kind of rehearsal is repeating the same information, what is called the rote learning, I mean, studying by heart, which is a way to learn, but it's not very effective. I mean, as you probably know, things are not really remembered in a very effective way, and they may actually be lost with time. Now, there are different kinds actually of rehearsal. Normally, what is called maintenance, I pushed the wrong one. What is called maintenance rehearsal is a kind of loop that allows the information to persist in short-term memory for a longer time than 2-3 seconds. Of course, I mean, 2-3 seconds is very short. In most of our tasks, we need the information to stay there longer. So we can repeat this information, we rehearse this information. Sometimes we do this actually implicitly, unconsciously, without even realizing. But this is a way to make the information persist. And another way is actually to refresh the information through usage. When we use the information, because we are processing it, then in some way the decay time is reset to the original value. So this information keeps staying there. But in the end, it will decay. Now, if you want to transfer information from long-term memory, there are more effective ways than just maintenance rehearsal. I mean, it's not clear how much and to which extent and whether maintenance rehearsal allows the transfer of information to short-term memory to long-term memory. But what actually does the job in a better ways is called elaborative rehearsal. Now, elaborative rehearsal means that we actually not only repeat the information, but we link to something that it's already in long-term memory. That's why when we study, if we just read a book, what we do, we just do a kind of very basic maintenance rehearsal. Maybe we reread the same sentence several times. But if we have next to us pen and paper, we try to convert what we read into diagrams, in something that links to what we already know, then this information will be actually more persistent, and then in the end will be transferred to long-term memory. Okay, so let's go on with this lesson of psychology. Now, there is also something else that occurs in long-term memory. We call it skill acquisition. What we transfer from short-term memory to long-term memory is actually information which is more declarative. So what makes up our knowledge? For example, we actually see that the dog has 4 legs, so we transfer this information, and we acquire the knowledge that the dog has 4 legs. Now, many things, however, I mean, if every time we want to retrieve this information, we have to reason and trying to navigate in semantic memory, things would be very, very slow in our processing. That's why we have actually another kind of memory, which is called procedural memory, which is the basis of skill acquisition. So you all know how to walk, but how did you learn how to walk? If I ask you, how do you walk? What is the process that allows your legs to walk? Right? It's something that you don't know, you're not aware anymore. But when you were a child and you learn to walk, you actually basically reasoned, even in an implicit way, trying steps and then verifying what is working, not working. So this is the process of skill acquisition. So this process is, at some point becomes like wired in your procedural memory, and they are processes which occur in a way automatically. The same for learning to ride a bike, even driving. So semantic memory is more associated to what is deliberate behavior. I make a decision, I have a goal in particular, we talked about goal, and I do something in order to achieve this goal. Procedural memory is actually what implements the automatic behavior. So when you start driving, I mean, if you are with your instructor, you actually think about what you have learned in the theory. Now I have to, it tells me to turn to the left. So now I have to lower the gear, slow down, stop, give way to the other side. Then I turn. Now, when you drive, you don't think about these things anymore, because this information is now in your procedural memory. So you do everything automatic. And in fact, you can use your short-term memory and other parts of your memory to do other things, talking with the person next to you. When you were driving, learning to drive, you were not able to talk with someone else while driving. You were very, very concentrated. Okay. Now, another important thing, of course, we build a kind of knowledge, our knowledge in semantic memory, but we want to be able to retrieve it because we need to use the information. So we have also a process in the other direction that transfers from long-term memory to short-term memory. And then in short-term memory, which in fact we call also, at least if we consider short-term memory together with the processes which act on it, we call it working memory, because it's what allows us to do whatever we do in the life. And in fact, together, let's say long-term memory and short-term memory, allow us to act on the motor system, to transfer information to the motor system, then which implements our action in terms of real muscle movements and so on. Okay, so let's go back now to the task, example of task, and let's try to see how we can describe the actual task. So here we have the example of the system. So this is the ATM, the physical system. We want to build up a task which matches that system. Then in the end, we will combine these two things and we will have a behavior which we can analyze. So we have a goal. And the goal is actually to collect the cash. I mean, the way we represent the goal in our notation is in terms of what are the achievements. So when we withdraw cash, our achievement would be to collect the cash. And when we achieve that, the goal will disappear. Initially, our goal in the short-term memory. So it's one of those 7 plus minus 2 items that are there. So we have to remember that we do this. How many times it happens to you to go to a room and then, what was I supposed to do here? Well, because for some reason, your goal has gone away from short-term memory. That's why. Of course, if you go back, maybe you do some other things, then something allows you to recall it back. But at that point, it has gone. So it occupies some space. It's obvious in short-term memory. Now, let's see how we describe the behavior of interaction. So one thing you can do, actually, if you see that there is a request for a card, let's call it request card, then we will insert the card and we will try to remember that we have to collect it in the end, because this is something that we have to remember, to recall. So this notation allows us to describe basically three things: perception, action, and information that here we store in short-term memory. So this arrow down means we store. Here we retrieve from short-term memory, but in this case, we don't retrieve anything. In other cases, we retrieve something. And then there is this arrow. What is on the left is actually enabling the application of the rule. What is on the right is actually the effect of the rule. So in this case, when we see that the card is requested, we actually insert the card and we try to remember to collect it. So we put it, remember, it means that we put it in a short-term memory. I will show you when I do the simulation how these things progress. But let's see another important rule. So this rule basically is what we have learned. So they are in some part of long-term memory. It could be procedural memory, it could be semantic memory, but they are in long-term memory, something that we know how to do. Now here, when we see a request of a pin, we are automatically in some way, I already said automatically, which means where this rule is, it's in our procedural memory, we enter the pin. In some way also this is automatic, because what activated is just a perception. So already we see that these two rules will be in long-term memory, but specifically they will be in a procedural memory. Then, of course, we can do many things with our ITM. One thing is to collect cache, so to withdraw cache. So if this is our goal, then when we see the cache, we will collect it. And this is the rule that expresses it. Now, this is based on a goal. Yes, there is a perception here, but there is also a goal that we have in mind. So it's something that we do deliberately. Now, there are quite a number of level of degree of being deliberate or not, but there is some deliberate, some will in doing it. It's not something that we do really automatic. Finally, we need to collect the card. And we have to remember, so we will do it if we are triggered by the fact that we still remember that we have to do it. But we might actually forget it. It's more difficult to forget to collect cache because that's our goal. Now, the point is that when we achieve this goal, and the achievement is when actually here you see, this is the achievement. When we perform an action that matches the achievement, the initial achievement, then what happens? This goal will be removed from short-term memory. Now, let's see really the simulation. So let's start from the beginning, just to go on through this. So at the beginning, what is enabled of these rules is actually the first one, because the first state of our system will be request card. Okay, so this is the initial state of our ATM. So request card, so this is the only enable rule. So what we do, we actually insert the card and we remember to collect the card. So this collect card will go to the short-term memory. So we have two items in short-term memory. Then the second thing, after we have actually inserted the card, the ATM move to this state. So what happens is that we see a request for a pin. So now this is our rule in long-term memory, which is enabled. So we enter the pin, and once the entering pin is detected, then we move, the ATM moves to the third state. So we'll check credentials. So this is an internal state. So there will be some interaction with the word, as we have seen in the previous diagram, which we don't see as a user. Once these credentials are actually checked and the the card is enabled, the pin matches the card, then the cache will be delivered. So the machine moves to this state. Now we suppose to have a specific order of these actions. Here, there is no order. I mean, whatever it is enabled, sometimes non-deterministically, because more than one might be enabled, whatever it is enabled, it's performed. But here there is a specific order. You see, I numbered it. So now the cache is delivered. So this rule is enabled because goal collect cache is here in short-term memory. This is the perception. So we collect the cache. And once we collect the cache, the goal will actually disappear from short-term memory. Why it disappears? Because it is achieved. And we see this matching allows us to see that the goal has disappeared. So what's going to happen now? Well, we have here collect the card. So in principle, we can collect the card because we remember. But what happens is actually sometimes, short-term memory is very short, very small. So we need to, when we complete, we achieve a goal, often we want to start to do something else. So if our short-term memory is too full, there is a possibility that not only the goal disappears from here, but also some other information which was used to achieve that goal disappears. So there is the possibility that also this collect card disappears from there. And in that case, what happens? Well, it happens that this rule is not enabled, and so we forget to collect the cache. Now, this might happen if the short-term memory is too full because we are stressed, because we are thinking about many things. So once we achieve the collection of cache, the short-term memory is empty, at least partially. It might be happening that something that we try to remember actually disappears. So that's why, not always, but in some situations, we might forget the card. Now, how do we solve this problem? How do ATM? Yeah. In fact, probably you are too young, but when I was young, this was actually the real sequence of an ATM. So the first thing, they deliver cash, and then they return the card. But now, once it was realized how many cards were forgotten there and confiscated, most of the banks, at least in Italy, most of the Europe, they swapped this operation. When I arrived in Kazakhstan, my bank actually used the new way where the operations are actually swapped. Then they changed for some reason. They went back to the old way, which is very annoying for me, but I manage always to collect my card. But I have a colleague, he's from the Netherlands, who got the card confiscated already twice. So anyway, as people in Kazakhstan say, that's Kazakhstan. I mean, locals say that. Okay, let's backtrack now. So this is clearly not enabled. We want to make it enabled. So we want to go back to the situation in which we are here. And we want to swap, as we said, these two different steps in the ATM. So we do it. Now, starting from this step, it's obvious that now we collect first the card. For sure, now collect card is still something that we remember. And then after that, we can remove it, and that doesn't harm anymore. And then we can actually collect the cash. And now the new ATM works without that mistake. And that mistake is very important. In fact, it is a common error, which is called post-completion error. Now, post-completion error occurs when user terminates an interaction with outstanding tasks remaining. So terminating interaction means that we achieve the goal. It emerges because the user cleared STM once the goal is achieved. how much it clears depends on the content, how much overloaded the STM is. So this error may or may not emerge. Now, in most cases, it will not, but in some cases, it will. Obviously, we have discovered the design principle. The goal must be achieved through the last task allowed by the interface, because in this way, if we achieve as the last task, we don't have anything else to do. We can clear our short-term memory and move to the next task. Now, the bank in Kazakhstan will give you a warning. Remember to collect your card, flashing. I mean, that's okay. I mean, it helps to reduce the likelihood to leave the card there, but doesn't remove the error. In fact, my colleague is not blind, is not deaf, but still he left twice his card there. So this is evidence that it's warnings help to reduce, but they don't remove problems. Okay, this is not a ad hoc example, because post-completion error occurs really in many situations, even in situations you never thought about. You have here a number of vending machines. What could be a post-completion error in the vending machines here? I mean, normally you put the money, you get the change, then you get what might happen?
To take the stuff that you want, but you don't have a care of the money.
Right. Yeah, exactly. Normally there is a sound, cling, 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 cling. So you will remember. That's a kind of warning, of course. But again, you might still forget it. Of course, a deaf person will forget it.
Yeah.
Well, as me, if there is a post-completion error, of course, if there is a situation in which this person is stressed. Okay, so we have, we want to purchase, but then collecting the change might actually not occur. Let's see another example, photocopy machine. How many times? Sometimes when I do to make some photocopy, I open and find things. And once I found a passport even. So I took it, I went to my colleague, can you show me your passport? Anyway, this is another problem. Here it's more difficult to solve it, because how do you solve it? I mean, in the vending machine, you could, extreme case, you could check the weight, I don't know, and not to deliver food until the weight in the, it's not worthy, because you have also to take into account whether it's more expensive to correct the error or to let the user doing the error. It is more, of course, for the ATM, it is important, because losing a card, my colleague knows it, it becomes a big hassle then to get it back. But here, how do you do it? Because I mean, it's not clear. And on the other hand, I mean, it's not something that, again, is very problematic, because normally these machines are not that public, that things can be stolen and taken it away. I mean, they're in institutions, so people take. And the passport, I took it to my colleague without any problem. Fridge, your fridge. How can you do a post-completion error with your fridge? Yeah, in fact, normally what happens in a fridge, if you open it, you take something, the door tends to close by itself. That's a mechanism to allow to prevent you from carrying out post-completion error. But of course, if the fridge is old and this mechanism doesn't work anymore, then you might do post-completion error. And in fact, in that case, it's very dangerous, because you will do it most of the cases, because it's not your habit to accompany the door of the fridge when there is a problem. So really, it is a problem. Okay, it's not really a safety critical problem, but still exists. Fuel tank in your car. When you refill the petrol in your car, what do? You open and you put.
Forget to close?
Forget to close. Okay. Now, there is a way, very easy way to prevent it. Now it's not used anymore because of the modern technology, but when I had my old car, I could never do it to forget it. Why? Because the same key to lock it was the same key to start the engine. And if you don't lock it, you couldn't remove the key. I changed car, unfortunately. Now I just have to to screw it. Nothing else. If I don't screw it properly, of course, I don't close it properly. I cannot close it properly also the cover. But the first time with the new car, I went to the petrol station. I was starting, then someone honked behind me. What's happening? And then he pointed. I went there, and it was actually laptop. Because I didn't have the habit to remember it. I was actually doing it because I knew that there was a key there already attached. But if there is no key attached, you don't think that you actually have to close. Or sometimes I remember it happened to me to actually go sit down, where are my key? And then, okay, went back, I closed. Okay, so this is another, still post-completion error, but there are many other things. Writing email. Well, yes, you forget the attachment because you have in mind to send the email. But also think about this. You write the email, then maybe you save it because you want to re-edit it. But then the fact that you have written the email actually have removed all information, even the information that you have to send it. So you will forget how many times you found in your draft folder emails, and actually someone told you, are you going to send me this email? Well, I sent it already. No. Then you look in the draft folder, it's there. But you remember to have written the email because the real goal is actually to write the content. Not sending is just a kind of post-completion error. Now, this is another thing which is actually difficult to manage because, yes, you can. In some cases, this is what's happening. The email, which is, for example, if you use Moodle, you can post a message, but this message cannot be saved. You post it, and then after a while, it is sent. You can delay it. You can post it immediately. So if you want to, basically, you post it, then after a while, you might re-edit it, but it will be sent automatically at some point. Of course, this is not convenient in some cases. So this is a problem which is difficult to solve, and it depends on the context. We are in this, since we are in terms of election, I don't know if I remember correctly, but I had the feeling once, and I did this because I was thinking that now there was election here, maybe you are not resident, so you didn't vote here, I don't know, in your uh, city. I remember once I participated to the local election, and I remember you could vote either for the party, and there were two parties, so put a cross, or you could vote for people, so put the names. But if you vote for people, if I remember correctly, the rule was that you had also to cross that party. At least, is it like this? So if you put the name of the person, but you don't cross, it's blank, right? Invalid. What is your goal in that case? Either to vote for a party or to vote for a person. If your goal is to vote for a specific person, you are likely to forget to cross because you write the name and then you forget to cross. And this is something that it's really, nobody could think about it, but I'm sure quite a number of null votes are due to this situation. So you see, even within the same task, you know how many ways there are to have a post-completion error. Now, there are two people online, I don't know whether here, online who actually were working at IMT in Lucca. There was a canteen there. I don't know whether some of you, Rocco, Claudio, remember how it worked. I don't know whether it works still in this way, but the way it worked, there was the bank, the place where the food was. You arrive at the beginning, you give your card, and then there were two people, one normally giving the food, and the other one processing the card. And then in the end, putting the card there. Now, when you're right there, you got the last plate. you achieved your goal. You forget that card. It happened to me, of course. And that was a big problem because I couldn't, the Mensa was closed, and then I couldn't enter certain parts of the building. If I went out, I couldn't go back. So it was really a painful thing. So I hope, Rocco, you have changed this at IMT. Okay, I have another interesting one. Baking a cake. So normally, what happens? You actually have to set a specific temperature to bake a cake. But a very professional advice is that if the temperature is 180 degrees, you should actually set 200 degrees. Then after you open the oven, the temperature inside will decrease. So you insert your cake, you close it, and you decrease the temperature. What could happen?
The cake to cook. Oh, you forgot the reasons.
You will forget to decrease. Sure. So in your mental protocol, you should actually do this. You should, when it is the temperature is reached, you should go there and immediately decrease. Now, it doesn't go down the temperature immediately, of course. You just might even not reheat anymore because the temperature is reached. So you open, you insert, and you close. Because if you actually insert the cake first, you are very likely to forget to decrease the uh, the temperature. So this is something, it happened in my family, let's say. That's why I put it here. And now, finally, I have another example, which actually I'm working nowadays with a psychologist. Now, in the world, there are quite a number of cases every year in which children are forgotten in car during summer, and actually many of them dies. Basically, in the United States, the average number of cases per year is 40 deaths for this reason. Now, together with the psychologist, we have actually checked about 160 cases of deaths over the last years in the US. And we try to analyze from the reports of the accident, what is the cause why the parents forgot the child. And not all of them, but some of them are likely to be post-completion error. I mean, those parents were going to a mall, their goal was to go to a mall, and for some reason, overloading in their memory, they forgot that subsidiary task to remove the child from the car. Not all of them actually are dead. So we found other situations. It's quite an interesting work we are doing at the moment. So the goal is shopping, but you forget to remove the child. This is a very serious problem because you have 40 deaths per year in the US, and some of these, I think we found about 1/3 are actually due to post-completion error. But there are other situations which are also safety critical. And the first time it was found out that post-completion error can occur can be the cause of a plane accident was in 2013. Before, it was never realized. So what happened? Planes are under maintenance very periodically. So what happened? A team made maintenance of a plane. So they have to do maintenance at the engine. They have to open the cover. Maybe they have to start the engine in some way, do some tests. Then they close the cover and they have to latch it. Okay, they have to lock in a way that it would, during flight, nothing would happen. Now, in this accident, the team forgot to do this. So basically, the fan cold doors were left unlatched on both engines. And what happened is that during the flight, they came out because of the air, and they damage the engine itself, which start burning. So now this is an accident that, I mean, it didn't cause any injury. The plane could fly back. And the report even doesn't really mention the post-completion error, but after the accident was completed, or the report was completed, it was actually revised and it was realized that this is actually post-completion error. And it was also found out that previous accidents are likely to be caused by this, also fatal accidents. So this is a really serious problem. Okay, so now we are ready to go into something slightly more formal. So we see clearly the notation in which we describe the human behavior. So basically, the notation is very simple because there is a simple structure. This is a structure of automatic action. So you see, you basically have something that you retrieve from your short-term memory, which enable your action. Then you have a perception that you can have of your interface, of the situation, your environment. Then you perform an action, and then you store some information in STM, in short-term memory. So here you actually, the rule says that you remove it. You might not remove it then in the syntax, you have actually to put this information both here and here. So basically you remove it, but then you put it back, which means you just read it without removing. So you can actually, with this kind of structured rule, you can describe also the situation in which you don't remove the information. But then you also have the previous, this case refers to automatic behavior. Here you have more deliberate behavior because you have a goal. A goal is something that is enabling the action, but it's not removed when you perform the rule unless you actually achieve the goal. For example, before you have seen that when you perform the action, which was the achievement of the goal was removed. Of course, these parts might be present or not present. You have seen rules in which this part was not present, this was not present. Even the action might not be present. So in that case, you have what is actually description of your attention. So you might have something here that triggers you, or a goal that triggers you to perceive something, so to focus on some of your perception. And then this perception is transferred. Maybe the same perception can be this stored information. So the perception is really transferred to short-term memory. So this is pure attention. Or you might do also some deduction, and then you already process and you transfer this process information in short-term memory. So you can describe attention, you can describe action. So these kind of rules are very flexible. You can see here you can describe inferences, for example, if you don't have anything, no perception, no action, basically you just transform this information into something else. So you do an inference. Here it's similar to an inference, but you have a goal. So it's really a planning of something you plan to do it. And here you have what is the more pure deliberate behavior. It's a behavior, you perform an action, deliberate because there is no perception that automatically drives it. And analogously, you can have things with automatic control. You have implicit attention, you see, in which you just transfer information without goal. Here, you transfer information with the goal, so it's more explicit. I mean, you look for the information you look for the perception. So you can do it deliberately or automatically. So here you can actually see better what are the things that the meaning of things. So here the perception on which you focus is actually your mental state, what you are thinking about, or here you have a current mental state. So you have ways in which I mean, this way allows you to describe many kind of thinking behaviors and actual behavior as well. So for example, an inference will have a premise here and a consequence here. Okay. So what is in this notation, what counts is the structure. Then you can be very flexible. Also the components, they can be represented in different ways. You can have an informal sentence describing what it's doing, and then you can use this notation informally, just to do reasoning. Just to, actually, I use this notation. I'm not sure whether you're familiar with cognitive walkthrough. So a way of inspecting behaviors of a user interacting with machine, similar to code walkthrough, but applied to the cognition. Well, normally it's done in a very informal way, but if you use this notation, you can capture more easily and, in fact, unambiguously aspects which otherwise might be up to interpretation, while in this way, well, the interpretation is only the one given by the rules. I'm actually using this in my class on human-computer interaction, so the students will do this cognitive walkthrough using also this notation. Okay, now we have been talking about, we have seen a simulation. Now we want to see better how we can actually verify properties of systems. So for example, if we consider our cash transaction at an ATM and the actual ATM, one property could be the cash is always delivered. So this is a property of the system, you see. And this is what formal verification used to do. You have a system, and you want to verify that the system does what it is the functional requirement. Or maybe the card is always returned. But this doesn't say whether the user actually interact properly, taking the cash, taking the card. So what system verification does, it verifies just the system. Normally, these properties are expressed in temporal logic. We have a formal model of the system, which can be a transition system, can be a rewrite system, can be many things, a Petri net. And then you have a model checker, which is a tool that, given the property expressed as a formula, and the model of the system tells you whether the property holds on the system, or if it doesn't hold, it provides a counterexample. So something, a kind of trace of behavior that tells you, well, that actually doesn't match the formula. So you analyze this behavior and you can try to discover why, what is wrong in your system and correct it. But of course, if you use, for example, this technique analyzing the system, you will see that ATM, both kinds of new and old ATM versions, work correctly because they both deliver cash, they both deliver the card correctly. But the problem is that if you put the user together, then the situation is different. And in fact, what we have been done is to try to verify the interaction. So the interaction means that we have properties like the user always collect the cash, or the user always collect the card. This is a kind of property we are interested in verifying. Okay, how do we do it? Well, now the formal model is the model of the interaction. So in parallel, we combine our BRDL model with the transition system, the Petri net, or whatever it is, the model of the system. And then we apply the model checker to this combined model plus the temporal logic. And we get a counterexample if the property is not verified. Okay, any questions on this? Now, of course, another thing which is quite important that we can do using this notation, now we move away for a while from computer technology, and we think about just the human and the world. Now, this is allows us to actually emulate experiments which have been done, or we want to do it, in cognitive psychology. So in particular, we want to try to verify, we have many theories in psychology. For example, I mentioned that how long does the information persist in short-term memory and without any rehearsal, nothing. Well, I put 2, 3 seconds, but no, not everybody agrees on that. And the experiments don't give actually a final answer. I mean, that's the most recent view, but in the past, it was even thought more than 30 seconds, around 10 seconds. So there is no final answer to this. What we can do, actually, we can try to, after building a model, as I have shown before, to try to give alternative semantics for BRDL. So with different time parameters, with different ways also, for example, how does closure occur? The fact that you remove information after achieving the goal. In which situation you remove also other information in addition to the goal. And in which order you remove the newest, the oldest. So giving these different semantics to our BRDL, you can actually emulate this possibility and then comparing these things with cognitive theories based on experiments. So you compare the in silico simulation with what you get in experiments with human beings. So, for example, as I said, all these parameters, you see this number here, can actually vary this parameter in a way to provide alternative BRDL semantics. Then you simulate experiments which have been done in reality, and you see which combination best match the results of the experiment. So you apply this in silico simulation to understand which are the most likely, most correct theories in psychology. This is an example. Here, we did it for this experiment. This is a famous experiment in which you actually ask a human subject, you show actually a number of let's say, 15 words. You see they have all the same length. You have to also to use words which are similar frequency because you don't want it, there are a lot of things to take into account. Here, these are put randomly. It's not really taught very much, but you see they are all nouns, normally concrete nouns, which have only 3 letters, so they are at the same level. So what is the result of this experiment? You ask people you show, let's say, a couple of seconds every word, and then you ask immediately after this presentation, the subject to remember, to recall, in this case, the words. What happens is that there is a tendency to remember the first words, primacy effect, it's called primacy effect, and the most recent word, so the recency effect. What is forgotten normally is the word in the middle. So you will try to find a strategy to remember as many words as possible. Which is this strategy? You might not do this consciously, repeating the word. So you rehearse the word. You start rehearsing the words, you repeat them mentally. You start from the beginning. So you will rehearse the first words. But then what happens? These words are too many, and then you don't have really time to rehearse the next. So the next words will stay there for these 2, 3 seconds and then disappear. So 2, 3 seconds disappear, 2, 3 seconds disappear. Now, if I ask you to repeat immediately, to recall immediately, well, maybe 2, 3 seconds are not all passed for these words. So you are able to remember the words that you have rehearsed and the most recent words because they have not decayed yet. They are still in short-term memory. Now, there are a lot of factors here also to take into account. Of course, I said the frequency of words, many things. So they can be a kind of effect in this experiment. But I mean, this is an evidence that there is a kind of way of rehearsal that allows you to remember for a longer time. And on the other hand, there is a decay of the information. Also, you can do another thing. You can ask the subject immediately after the presentation to actually count, for example, backwards 10 to 0. So let 10 seconds pass. And what would happen in this case before doing the recall if you ask the subject to do this? What do you think? Remember, why do you have this recency effect? Because these are very recent. But if you ask the subject to count, well, counting means that you cannot you are using the short-term memory to do discounting. So you don't have space in short-term memory to do rehearsal anymore. So whatever rehearsed, you have rehearsed, but the last word will actually tend to go away because more than 3 seconds have passed, so some of them will disappear. And if you ask actually to count 30 to 0, it has been found that basically the recency effect disappears. So again, you see, there is evidence that this information is persists in short-term memory for a short time. So what we did, we actually modeled this mechanism, and we are now trying to compare it with experiments. We want also to do experiments that match our in silico simulation and see whether which way, with which parameters we try to calibrate it in order to understand exactly which are the time, even the time of persistent in short-term memory, how the time increases through rehearsal, all these kind of mechanisms. Now, in fact, this word we said decay. So basically, there is okay, some people interpret this experiment saying primacy effect means that the information is actually transferred to long-term memory. But this is not really true because, after 10 days of these experiments, you don't remember these words anymore. It's something more, not very short-term, but something in between. And that's why recently there is also a theory that there is a memory in between, or there is a kind of continuous between the two memories. So we are trying to model these different aspects in order to understand whether how this can be explained in terms of modeling in the best way. Now, we talked about skill acquisition. What can we see about skill acquisition? Well, one thing is that, you see, skill acquisition is this process in which semantic memory, the information moves from semantic memory to procedural memory. So when you learn to drive, this is what happens. Some information migrates from one to the other, and it's transformed in a way that is performed in an automatic way. But an important thing is that actually it's fundamental to have a procedural memory, because otherwise our activities will be very restricted if we have to think every time we drive, all the rules. We need to do things automatically. But in some situations, this also leads to errors. And this is what it is important. For example, procedural memory may erroneously take over on our decision-making process. Imagine that you drive to office every day, but then on Saturday you want to drive shopping, you don't go to work. And suppose the supermarket where you go is halfway through between your home and your office. What is likely you do, especially when you're stressed? Well, you find yourself in the office, not at the mall where you want to do the shopping. Because the procedural memory, going to office is something automatic. You do it automatically. And if you have this goal to go shopping, it's likely that the procedural memory take over, and actually you find yourself to the office. Actually, something like that happened to me. Last semester, I used to have a class very late, around 5 p.m. This is especially in winter, that's a time when it's dark, you go home. Now, going out of my building, the classroom was on the left. My home was on the right. How many times? Twice actually it happened. I went down and turned to the right going home. Then halfway through, I remember, once I actually got home really. So why? Because it's only twice a week that I have to go to this classroom, and I have to make a decision, turn to the left. While if I think about something else, I would go to the right and go home. So think about your personal experiences, and you will find many of these things happen. Okay, so another important thing is matching retrieval experiment. So as we said, we retrieve information from semantic memory. Now, there is a famous experiment done in the past that has provided evidence that our semantic memory is a kind of network. So if we think about what we know about animals and dogs, for example, we know that dog barks, a dog has 4 legs, has a tail, but we also know that the dog is an animal. And animals have some attributes like moves, breathes, which can actually inherited by dog. You don't. A question is our memory to replicating all this information for every item? So is it attached also to dog, or we actually try to retrieve interpreting this hierarchy? And this can be very complicated, you see. We can also link to other knowledge domain. For example, Lassie was a collie, but it was also an actor, a character in a film, so we can connect all. It can be, we try to actually model quite a complex semantic network. But this work was actually done quite long ago. There was an experiment by Collins and Quillian in which a number of subjects were asked questions referring to, they actually built a semantic network about 800 concepts. And for example, if we ask a question, can a collie breathe? If we assume that this information is not replicated for dog, for sheepdog, and for collie, what's happening is that the human being has to go through this kind of path in order to answer the question. While if we ask, does a hound track? Well, that's immediate because it's already an attribute of hound. Hound, I don't know. How do we pronounce? Can you check with the ChatGPT? Hound, I think. Okay. So what happened in this experiment in 1969 is that subjects take longer to answer the first question with respect to the second one. So this was an evidence that there is some kind of semantic network. Of course, there are other factors affecting, so it's not necessarily just that factor too. There were some anomalies, some obvious, some others still under investigation. But in reality, they were not even questioned. Now I put a question because it's easier to see, but the real experiment gave statements, and the user had to, it was in 1969, so he had 2 buttons, left no, right was yes, saying is it a true or a false statement. So for example, the statements were a collie breathes, so you would say yes, okay. So and there were some anomalies, but I don't want to go into this. It's not really fundamental. Okay, now, so all what we said now helps a lot cognitive psychology, but it's done through in silico simulation. What can we do actually with model checking? So really verifying property of the human being in order to support psychological theory. Now, we want to see the human behavior acting on the world. Now, the world is our environment, and basically, we do the model checking considering these components, these 2 components together. So the human model is expressed using BRDL. Then there is a model of the environment, again, could be any formal model using process algebras, Petri nets, rewrite system, and so on. And then we do model check. Now, here the temporal logic formula describes a kind of a high-level psychology theory. So something that normally is expressed conceptually or as a taxonomy by psychologists. And what you get is actually whether the property holds or a counterexample that the property doesn't hold. So this is the general schema, but it's a schema that I applied to a real example. Working, in fact, this was quite the work I did some time ago when I was still in Australia. So it was done together with some people working in a cognitive psychology research center. And these people developed a simulator for air traffic control. And then they asked people who were not really air traffic controller, but I mean, normal people to use it. And then what they tried to do, they wanted to see what was the situation that caused to a failure of the task, because the task consisted in making sure that the minimum distance between plane was not violated. So if this task failure occurred, what was the source? So observing these people, they created a taxonomy of possible mistakes. And then what we did, we formalized this taxonomy in terms of formally in temporal logic. What we wanted to prove is that the task failure decomposition provided by them was actually correct. So they provided different kinds of error, and they said, these are the errors that might lead the operator to do the mistake. So we formalized these errors, we formalized the task failure, so the violation of the distance, and we wanted to prove this formula. So if a task failure occurs, then one of these errors has to occur. So we applied the model checker, and we got a counterexample. So we studied this counterexample, we found out that there was a possible behavior which the psychologists didn't see. So we completed the formula, and then it worked, obviously. So at this point, this formula with the new error added as a possible error was actually satisfied. And then with the psychologist, we worked at the interpretation of this error. So it was quite an interesting thing. Now, we are using a similar approach now for the hot car example, the hot car death. Because here the situation is a bit different. You have parents and you have a very specific scenario. Actually, each of those 160 cases is a different scenario. But we classified some of them corresponding. So this error I will be the same for a number of scenarios, but not for all. We have a number of errors. One is post-completion error, but there are others. So we want to see that the task failure, so forgetting to remove the child, actually causes this error, this specific error, okay? Under the specific scenario. So when we have classified the scenario as a post-completion error, we want to verify that this is correct. So this is actually ongoing work still. Okay, so let's conclude. Now, I didn't mention the implementation, but this is implemented using the Maude rewrite system. I said there are many, you could use other formal methods, but Maude is quite useful because being based on rewriting rules, it is very easy to implement this rule that I described for the behavior. Then we have different ways also to model the system. We put these things together and we use the model checker available in Maude to perform the verification, the simulation, the verification. Also, we use the real-time version of Maude, actually. I didn't mention it here, which allows us also to check all those timing constraints, timing aspects that I mentioned. So, as I said, we also use the BRDL with independent of the implementation, of course, as an informal modeling and reasoning tool. And this can be actually used in making unambiguous many things which otherwise psychologists would describe in natural language with all possible ambiguities. But as a formal tool, we have seen that it can be used for formal verification of interactive system, model checking. We can perform in silico experiments on human cognition using the simulation, but also we can verify high-level psychology theories. We have seen the description of the task failure and its decomposition formulated by psychologists, and we have verified and corrected it using model checking. And now what we are doing, actually we are trying to implement, extend, of course, BRDL. We are working a lot now with motivation, emotions, because emotions are an important part. And we are going to work with problem solving and decision making, because I mean, reasoning plus emotion can allow people to do actually decision making. And we want, of course, to implement all this in Maude. We want to match, of course, we are doing it. This is a very time consuming, matching experiments with humans, comparing alternative theories. This is a very long-term work, and it will be done over the next years, hopefully getting also some grant that will support. Another important thing we are working, we did some, to some extent with some students. I mean, this is mostly a way of making this methodology available for domain experts. So we want to have tools which allow the domain expert to easily model, so graphical tools that allow to using also sometimes converting automatically some description in natural language in order to create a model. Again, this is a work that is going to be done on the long term. Okay, so just to conclude, I give you a couple of references which are very informal. I mean, the first one is the first introduction of BRDL 5 years ago. And this is actually a paper which we describe a course given to a school in which BRDL introduced, but especially all its possible use. So it's again informal, but it contains also a lot of references to more formal works in which these things are implemented. So that's it. Thanks for your attention.